All right, so we're going to start talking about rate laws. Yesterday we talked about reaction rates, which is just how quickly a reaction happens. Rate laws is basically we're looking at the whole system of both reactants and we're seeing how does one affect the other. Okay, that's essentially what a rate law is. But so far, all we've been doing is looking at the reactions that are going in one direction. We've looked at the reactants forming some products. But in all reality, reactions are reversible, right? Once enough products are formed, then those products start interacting with each other, and they'll start going back the other way. So in all reality, when you get enough products, in this example, NO and O2, when you get enough of those products accumulating, they will start interacting, and then they'll start forming NO2 again. And so then your reaction will look like that. Right? What was your products now become your reactants, and you form that NO2 as a product. Okay, that's what happens in reactions. But there's a kind of a problem when that happens. Okay, so when this happens, the concentration of our initial reactant, so NO2, okay, when we start to have this reversible reaction, the concentration of NO2 starts becoming dependent on both the rates of the forward and the reverse reactions, right? When we start having forward and reverse reactions happening, the concentrations start becoming dependent on multiple things, which just adds big-time complexities to our problems, right? So we try to avoid this, right? We don't want to have to figure out the rate law dependent on a bunch of variables, right? We try to get it as simple as we can. So when we're looking at rate laws, our goal is to avoid those complications by just looking at reaction rates under conditions where the reverse reaction is really not happening yet, okay? Or it says it's making a negligible contribution. So we want to try to study reaction rates at the very beginning, right? That's pretty much it. We want to study reaction rates at the very beginning of a reaction, because if we don't study reaction rates at the very beginning of a reaction, that means that products are being formed and then maybe reforming back into our original ones, which messes with that concentration again, right? There's just a lot of factors that could happen if we don't study reactions at the very, very beginning. So that's the goal, right? We study reaction rates at the very beginning of a reaction so that our production or our products reforming is having like a negligible contribution, right? Does that kind of make sense? Okay. So if we choose conditions where the reverse reaction, the reaction rate will depend only on the concentrations of the reactions. Okay, we said if we let reactions go too far, concentrations start depending on both the products and reactants happening. But if we study them early in the reaction, they're only going to depend on the concentrations of the reactants, which is what we want. Okay, so when we do all this study with rate law and rates of reactions, we want to be able to look just at what's happening with the reactants and how are those affecting our overall reaction. Okay, so the rate law, that's our goal for today, is to study something called rate laws. They show how the rate depends on the concentrations of the reactants. Okay, how the rate of reaction is dependent upon the concentration of the reactants. So what that means is that we're going to study if we put in twice as concentrated of one of my reactants, does it make my reaction go twice as fast? Or if I cut the concentration of my reactant in half, does it speed up my reaction? Right? That's the relationships that we're trying to study in this. We're going to be able to look at sets of reactants and see how do they affect one another. Okay? That's kind of the goal of a rate law, is to see how do these two reactants and their concentrations affect the overall speed of the reaction. Does that kind of make sense? Okay. So if we look at this equation here, the decomposition of nitrogen dioxide, that's the one we've kind of been looking at this whole time. The rate law is given with this basic formula. Okay, this right here is called a rate law. Okay, it's called a rate law. This is called the rate constant. What do the brackets mean? Remember, we talked about that yesterday. What does it mean for something to be in brackets? Good. It means we're talking about the concentration of that particular substance. And then N is given in an exponent form, and N is called the order of the reactant. And so we'll talk about what that means and how we calculate the order of the reactant. Okay? The order of the reactant basically gives us a scale on how much does this one affect other reactants or the speed of it. Okay? If we had let's say that we had a reaction that had more than one reactant, right? This reaction only has one reactant listed. Let's say we had a reaction that was A plus B yields AB. Well, the rate law for this reaction would be R equals K times the concentration of A to some exponent times the concentration of B to some other exponent. Does that make sense? We would keep listing however many reactants we had, and we multiply them together and we give them each their own exponent. That'll tell us the order for each of those reactants. Okay, so we're going to be able to study and calculate the order or the exponents for each of those. We're going to be able to solve for what the K rate constant is, all that kind of stuff. Okay, does that kind of make sense so far? That's the general formula for the rate law. Is it going? Okay. So here's a couple things that we want to talk about with rate law. Okay, we gave you the basic formula here. Concentration of the products do not appear in the rate law. So maybe underline that, highlight it, whatever you want to do with that. But the concentrations of the products do not appear in the rate law. Okay, the reason for that is the reaction rates are studied under conditions where the reverse reaction does not contribute to the overall rate. All that means is that we're studying them at the beginning, right? Before that many products are formed, okay? K is the rate constant. It can only be determined by the experiment itself. So you can't theoretically calculate K without running experiments and getting data, right? We're not going to physically run the experiments. We're going to do problems that have the experiments already run. But you can't calculate K without having the actual rate data. So it's got to be done experimentally to find that. The same is true for your order of your reactants, that exponent. You have to have the experimental data in order to be able to calculate those values. So that means that in an equation, let's say, if we had if we had NO2, like in a different reaction, NO2 plus something else, NO2 would not necessarily have the same order in every reaction. It might be different depending on what it's reacting with. Does that kind of make sense? Okay, a little bit. So it's very, very much reaction and experiment dependent. Okay, two types of rate laws. We're going to focus mainly on the first one listed here, the differential rate law. It's what's just normally called rate law, okay? There's nothing really special about it. It's just that that's the one that is the most common. It's called the differential rate law, but you'll just hear me refer to it as rate law, okay? It shows how the rate of the reaction depends on concentrations. That's the whole goal of the rate law. The integrated rate law shows how the concentrations of particular species in the reaction depend on time. So it's kind of the inverse of that, and we're not going to get to that today. Today we're just going to focus on the differentiated rate law, okay, which is the basic one, the one that we'll study kind of the most. Okay. So I want to do a couple of these next bullets are really just summary things that I want you to just hear or at least read. And then we're going to get to the actual math part of it. Okay, so summaries of rate law. We typically consider reactions under conditions where the reverse reaction is unimportant. So our rate laws will only involve concentrations of reactants. I think we've said that like 3 times now. Okay, so we know that the rate law only involves reactants. Okay. Because differential and integrated rate laws are given in a well-defined way, the experimental determination of either of the rate laws is sufficient, which means if it asked you to solve for rate law, you would never have to do like both. Okay, we're just learning differential today, so it doesn't really make a difference for us today. But in doing rate law calculations, you would never have to really solve for both. Okay? Experimental convenience dictates which type of rate law is determined. So you're going to figure out, are you really studying concentration or are you studying time effects, right? And that will pick which one you really need to study. And then knowing rate law for reaction is important, mainly because we usually infer the individual steps involved in the reaction from the specific form of the rate law. So if we look at how concentrations affect the rate of a reaction, we're able to look at individual steps a little bit closer and find out how the reaction actually takes place, right? Is there a lot of involvement with these two species first, and then a third one comes in, or whatever it might be, okay? All right. Finding the order of the rate law. So that's like the exponent, right? When we had that rate law, we listed it as R equals K. Where are we going to go? R equals K times the concentration to the N power. That is the order, right? The exponent is like the order. When we determine that, we're going to determine it experimentally. So we're going to get experimental data of people that actually tested the rates, and then we're going to look at reaction concentrations and their relationship to one another to be able to determine that order. Okay? I know this is still, like, I know it does seem like really abstract right now, and it's crazy. I understand, but I think it's going to come together when we actually start looking at a problem. So hang in there. We're going to get there. Okay, this is the method we're going to use to figure out the rate law. Okay, we understand what a rate law is at this point, or we should be close. Now we're going to figure out how we can find the forms and the final rate law. Okay, the value of the initial rate is determined for each experiment at t equals 0, or as close to the beginning of the reaction as possible. So initial rates, those might be measured in moles per liter seconds, right? It's how fast that object is being consumed, right? How fast is my reactant being consumed? That's our reaction rate. That's what we did yesterday, right? The change in concentration over change in time. That's reaction rate. Okay? So someone will have collected these initial reaction rates. Once they have that reaction rates, then they will conduct experiments that use the same reaction but at different concentrations. So they'll start with one of their reactants at a more concentrated level, right? And they'll run the reaction again to collect that reaction rate and figure out, did that increase in concentration really affect how much, or did it affect the rate of the reaction, yes or no, right? Those are the things that they're going to see. They're going to run several different experiments with several variations of concentrations to see, did it go faster, did it go slower, did it go the same, okay? And then we'll compare results to see how the initial rate depends on the concentrations for each one. All right, so let's look at just a quick example here. This is the one given in your book, so I'm going to talk through this just a little bit, and then we're going to watch a con video to go through it just a little bit more, okay? So we've got this reaction that's 2N2O5 that breaks down to form NO2 and O2. In this reaction, O2 escapes from the reaction, so it won't react with N2 to make the reverse reaction relevant. So in this case, there is no reverse reaction for us to worry about, but they're still going to collect the data at the beginning, okay? Using this graph, the reaction rate of N2O5 was calculated at 0.90 molar and 0.45 molar. So I'm going to draw just a little bit like of a table up here and say in experiment 1, our concentration was 0.900 molar. In experiment 2, our concentration was 0.50 molar. Okay? And it said the rate was found to be 5.4 times 10 to the negative fourth. And then during the second reaction, the initial rate was found to be 2.7 times 10 to the negative fourth. Okay, so let's look at the relationship between those two experiments. what happened to the concentration between the first experiment and the second experiment? How did they change the concentration? Yeah, they divided by 2. So they started with half the concentration in the second experiment. Remember, these are 2 different experiments. So the first one, they started at a standard of 0.9. Second one, they moved it down to 0.450. Are the rates the same? No, which means the concentration change did have an effect. And so what's the relationship between the initial rate and the second rate? It's what? It's pretty much half. Exactly, right? So do you see how half the concentration led to half the rate? Right? Half the concentration led to half the rate. So that is what we would consider a first order, right? This would be considered a first order reaction, or there would be a first order on that form. So if we would go to look at our rate law, we'd say K equals concentration of N2O5, and it would be considered a first order reaction because these two are equal to each other, right? The relationship was the same. When we cut the concentration in half, the reaction cut in half. So it's got like what am I trying to think about? A direct correlation, right? You got it. So, there's going to be a little bit of another way for us to look at this, and that's what I'm going to show you in this next video here. But in the previous reaction, the rate was halved when the concentration was halved, and that means the reaction depends on the concentration of N2O5 to the first power. So that's what we talked about. It's called the first order rate law, or the first power. And we're going to look at all different versions of these equations and how they're going to affect that exponent right there. If it's a first order, if it's a second order, all that kind of stuff. Okay? So I want to, we don't need to talk about that, I guess. I just want you to notice that the coefficient and the order of the reaction don't have anything to do with one another. The coefficient in the reaction was 2. That does not affect the rate order at all. Okay, so don't worry about that part. All right, I want to pull up this video because I want us to watch this part of it from Khan because I think they do a good job of explaining it. So let me get this pulled up here and hopefully it'll work for us.
Concentration of nitric oxide to some power x. Now we don't know what x is yet. We also know the rate of the reaction is proportional to the concentration of our other reactant, which is hydrogen. So we put hydrogen in here, but we don't know what the